In this video, we're going to define a closed set in a topological space and do some examples. So our definition, a subset F of a topological space is closed if its complement, X minus F or F complement, is open. Recall this is exactly the same definition we gave in a metric space. So here's a few examples. Let's let X be any set. So what are the closed sets in the discrete topology for X? Recall that in the discrete topology, every set is open. Secondly, if X is any set, what are the closed sets in the indiscrete topology, also called the trivial topology? So the trivial topology, we could call it tau prime, consists only of the empty set and the set X. Those are all of the open sets or all of the sets in the topology tau prime, called either the indiscrete or the trivial topology. Last example here, we showed that the collection of sets, empty set, set containing B and C, and the set containing A, B, and C, is a topology for the set A, where A is just the points A, B, and C. So what are the closed sets in the topological space AS? So pause, think about those three examples, and we'll talk about them together. Okay, so if X is any set, what are the closed sets in the discrete topology? First of all, like the discrete topology, so let's say tau sub D is all A such that A is a subset of X. So absolutely all sets are open. All sets open in the discrete topology, or all subsets are open in the discrete topology. So let's say that, let's suppose that B is a subset of X, then B complement is also a subset of X, which implies that B complement is in the discrete topology. That is B complement is open. Therefore, therefore B is closed. So any arbitrary set is closed in the discrete topology. Every set is closed in the discrete topology. So in the discrete topology, every set is open and every set is closed. As we said, in the trivial topology, the only open sets are the empty set and the entire set X. So those are the only elements of the indiscrete topology or the trivial topology. So if we want to look at the closed sets, we can just take the complement of each of the open sets. The complement of the empty set is the whole set X, and so that is closed since the empty set is open, and the complement of the entire space, that's the empty set, and so that is closed as well since its complement X is open. So what are the closed sets? The closed sets are just the empty set and the entire set X in the indiscrete topology. Last example here, we showed that this is a topology for the set A consisting of A, B, and C. So what are the closed sets in this topological space? A set is closed if and only if its complement is open. So we can just again look at each set individually and look at its complement. So the empty set complement is the whole space A, B, and C, or in other words, A. Our next B complement is equal to, let's see, just A and C, and BC complement is equal to just the point A, the set containing the point A, and A, B, C complement is the empty set. So the closed sets are exactly those: A, the empty set, A and C, and A. Here is a theorem about closed sets in a topological space. So closed sets in a topological space always have the following properties. First, the set X, the entire set X, and the empty set are always closed. We saw that in each of the examples we looked at above. Let's just see why one is true. Well, the complement of the empty set is the entire set X, and because the empty set is open, that means that the set X is closed. And the complement of X is the empty set. Again, in any topological space, by definition, the set X and the empty set are open, therefore their complements are closed, so this is closed as well. So 1 is pretty quick. 2 is quick as well. We'll just do a sketch. The intersection of any collection of closed sets is a closed set. So suppose that the collection F sub alpha is a collection of closed sets. So it might be a finite collection, an infinite collection, could be countably infinite or uncountably infinite. Then the intersection of these F alphas, well, we want to show that it's closed. To show that it's closed, we can show that its complement is open. So the complement of that, by De Morgan's laws, is the union of the F alpha complements, so unioning the complements individually. And now, since each F alpha is closed, that means each F alpha complement is open. And we know that arbitrary unions of open sets in a topological space are open. So by def of a topology, we could say it 2 different ways. Either an arbitrary union of elements in the topology are in the topology, in tau or in tau, or arbitrary union of open sets are open. So by definition of a topology, because each F alpha complement is open, union of the F alpha complements is open. And so we see that this set is open, therefore this is. So this arbitrary intersection F alpha complement is closed, is open, and therefore the intersection of F alpha is closed. For part 3, the union of any finite collection of closed sets is a closed set. Again, we're just going to use De Morgan's laws and the definition of a topology. So in the definition of a topology tau, the finite intersection of open sets is open. So let's see. Let's say that F1 through Fn are closed. Then that means that Fi complement is open for each Fi. So the finite union I from I equal 1 to n of Fi complement, we're trying to show that the finite union is closed. This would be true if and only if its complement is open. So this is equal, again, by De Morgan's laws, to the intersection from I equal 1 to n of each Fi complement. And because each Fi is open, this is open. It's a finite intersection. And this tells us that, okay, we've got this set is open, this set is open, so the complement of this union is open. Therefore, since the complement of the union from I equals 1 to n of Fi is open, that means that the union from I equals 1 to n of the Fi is closed.